Assalamualaikum and hi to all. So this is the third video for BMCG 3723 heat and mass transfer force convection external. So in this video I'm going to explain flow across cylinder and sphere. So flow across cylinder and sphere. So this kind of thing is we frequently encounter in many heat transfer system. As I put here, for shell and tube heat exchanger, pin fin heat sink for electronic coolings, and many other application. So here for cylinder and sphere, the characteristic length is the external diameter, and the critical Reynolds number is considered as 2 times 10 to power of 5. So for flow over a cylinder and sphere, we have a complex flow pattern and it depends on the Reynolds number. So I put here, there is a 3 figure for 3 types of flow. The top one is the laminar flow, and then the second one is where there is a separation behind the cylinder, and then there is a wake region for periodic vortex. So for laminar flow, it happens at low upstream velocities for Reynolds number less and equal than 1, where the fluid is completely wraps around the cylinder, and for these cases within the Reynolds number less than 10, the friction drag dominate the friction coefficient. And then for the second figure, which is there is a separation region at higher velocity, the boundary layer detached from the surface, forming a separation region behind the cylinder, as I shown on your left hand side, the middle figure. So we have a separation region, and at high Reynolds number larger than 5000, so pressure drag dominates the drag coefficient, which is for this case of flow. And then another one is the flow in the wake region is characterized by periodic vortex formation and low pressure, as I shown in the last figure. So periodic vortex and in the wake region. So this happens at intermediate Reynolds number, and we should consider both pressure and friction drag. Okay. So I put a note down there. The nature of the flow across a cylinder or sphere strongly affect the total drag coefficient CD. So before you identify or determine the total drag coefficient CD, you need to understand first the Reynolds number across the cylinder and the flow, which region of flow happen across the cylinder before you can identify the total drag coefficient. So this is the figure of CD versus Reynolds number. In the y-axis is the CD, and then in the x-axis is the Reynolds number. I put a red dotted line to show where the creeping flow, separation start, vortex shedding start, and where is the turbulent flow. So for Reynolds number less or equal than 1, below than that is the creeping flow, and the flow is as shown in the figure. The first figure on your left, the first figure start from the left. So the flow is wrapped around the cylinder, and then at Reynolds number approximately 10, separation starts as shown in the second figure. So we have separation behind of the cylinder, and then at Reynolds number approximately 90, we have this vortex shedding started. As shown in the third figure, we have a circulation behind at the wake region behind the cylinder. And then within the range of Reynolds number 10 to power of 5 to the 10 power of 6, we have the turbulent flow. As you can see, the flow behind the cylinder is extremely complex. Effect of surface roughness. Okay. In general, it increases the drag coefficient in turbulent flow, but this kind of thing is special for the case of streamlined body such as flat plate. So for the blunt body, which is a circular cylinder or sphere, the phenomena is different, where the surface roughness may actually decrease the drag coefficient. As you can see in the figure of CD versus Reynolds number, we have a solid line of epsilon divided by D, which is the relative roughness, is equal to 0 for smooth surface, and then another one is golf ball, as been labeled in the figure. So you can see, since the golf average Reynolds number, the golf ball travel is around 4 times 10 to the power 4. So they design a dimple throughout the golf ball so that the drag coefficient decrease significantly at this value. And you can see there is a significant decrease in the CD for golf ball compared to the smooth surface, where the significant decrease in the drag coefficient for smooth surface happen only at the Reynolds number of 4 times 10 to the power 5. So this phenomena can be explained by the as a note put here, this is done by tripping the boundary layer into turbulence at lower Reynolds number, causing the fluid to close in behind the body, narrowing the wake and reducing pressure drag considerably, which explained by figure as in your right hand side, the top figure is for the smooth surface, and then the bottom one is the golf ball. You can see the wake region for smooth sphere is larger compared to the wake of the golf ball. So this is the reason why the drag coefficient reduced significantly at the same Reynolds number. So actually in this section, we are interested in the heat transfer coefficient. For flow across cylinder and sphere, in general, involve flow separation, which is difficult to handle analytically. The local Nusselt number around the periphery of cylinder subjected to cross flow varies considerably. So you can see on your right hand side, there is a figure of Nusselt number in the y-axis versus the theta from stagnation point in the x-axis. So this theta is the value as shown in the circle at the top of your figure. We have this distance of the d is the diameter of the cylinder, and the theta is as shown in the figure. So for small theta, the Nusselt number decreases with increasing theta as a result of the thickening of the laminar boundary layers. So within the range of 0 to 80 degree of theta, you can see throughout the Reynolds number, it start from high value and keep on decreasing until it reach a minimum value within the range of 80 to 90 degree of the theta from stagnation point. So the it reached minimum because of two things. For low Reynolds number is due to the separation in laminar flow, whereas for high Reynolds number is due to the transition to turbulent flow. So again, with the Nusselt number versus the theta from the stagnation point, so I put a few label there. We have first minimum Nusselt number, and then second minimum Nusselt number, and then we have okay, so we have this blue dotted line and red dotted line in the box. So okay, first I'm going to explain the two Reynolds number of 10,000, 100k, 100,000, Reynolds number 100,000 and 70,000. As you can see, it reduced at the low or the small value of theta, and then it reached minimum, first minimum of Nusselt number, and then it keep on increasing for 80 to 160 degree of the Nusselt number. So this is due to the intense missing in the separation zone. Whereas for the rest, we have a significant increase within the range of 100 degree to 120 degree, which is in the dotted blue line groups circle, so rectangular actually. So we have this which this is due to the transition from laminar to turbulent. And then we have the red rectangular, where the Nusselt number decrease significantly to a minimum, second minimum Nusselt number. So this happened due to the thickening of the boundary layers. And then we go to the 140-degree for turbulent flow. We have the Nusselt number reach a second minimum. This is happened due to the flow separation point in the turbulent flow. So actually, for the figure that I showed previously, is for the local heat transfer coefficient. Now we look into the average heat transfer coefficient across the cylinder. So from Churchill and Bernstein, we have this Nusselt number. It is given as in this equation, and you can see it is valid for Reynolds times Prandtl number for larger than 0.2, and we should evaluate the film temperature as the average temperature of the surface temperature of cylinder and then the surrounding temperature. And then we have another flow for sphere, which is given by Whittaker equation as shown here below, and it is valid within the range of 3.5 of the Reynolds number, 3.5 to 8 times 10 to power 4 of Reynolds number, and 0.7 to 380 of the Prandtl number. So these two correlation are accurate within plus minus 30%. So in order to create a more compact correlation, we use this equation for Nusselt number of cylinder equal to H, convection heat transfer, and D, diameter of cylinder, divided by K, which is the thermoconductivity of the fluid, equal to C, which is the constant, and Reynolds number, power of M, also a constant, and Prandtl number with the power of N. Here N is equal to 1 over 3, and they experimentally determine constant C and M, which are given in table 7.1. On your right hand side, we have a few cross section of the cylinder, and from there you can know the value of C and M, which is stated in the equation of table 7.1. Although you can use this equation, but mention here that the equation for cylinder is more accurate by Whittaker and Bernstein equation, and you should use this equation whenever possible. So this is the end of third section of forced convection external. And for further understanding, you should look into the exercise and try to do it. And hope you enjoyed this video, and thank you.